All right, so this is going to be another problem involving representing functions as a power series. This one's a little bit more complicated, so that's why I made a video for it. But it basically has this f of x function here, and it's centered at x equals 0. Now, we want it to look like that geometric series, where if you remember, it has that a over 1 minus r. So we want the function to somehow look like what I just wrote down here in red. So what I'm going to do here is actually factor out this bottom really quick for the f of x. And we end up with something like that. Now from here, again, we want it to be where there's something that's resembling a 1 minus r in the bottom. And you can this kind of hints at where we're going here is you can use partial fraction decomposition on this problem to get something that looks like that 1 minus r. So it's just going to be a over x plus 2 plus b over x minus 1. So this is really similar to that partial fraction decomposition that we used with integration, only this time you're using it for power series. Okay, from here we need to figure out what a and b are. Well, there is no x up here with the 3, so basically ax plus bx has to be equal to 0. Okay, and basically what I did to get the ax, I just multiplied it here, and then I did the same thing with the b. That's just for the x. Okay, for the constant terms, it's going to be a times this -1, so it's negative a, plus, now we're going to do this b times this 2 here, so it's 2b. Now that needs to be equal to this 3. Okay, there's no x term up here, but there is a 3. So the blue represents the constants, the green over here represents what the x terms are, the terms that have an x in them. Okay, from here I can factor out an x, and you have a plus b is equal to 0. So in this case, a is going to be equal to negative b. Now what's also true is that negative a is equal to b. So what I can do is substitute for that right up here. So now you're going to end up with b. This can be represented as b. So now you have b plus 2b equals 3. So that's just 3b is equal to 3. So b is equal to 1, which means a is going to be equal to -1. So now what we can do is we can break up this f of x function to be two functions that look like this up here. So it's going to be -1 over x plus 2 plus 1 over x minus 1. So now I'm going to rewrite both of these so they match more what this geometric series looks like up here. So we basically need this green, this first green part right here, to look like what we have up here. So I need that 2 on the bottom to become a 1. So what I'm going to do is factor out a 2. So you're going to have -1 over 2. Now if you factor out a 2, you're going to end up with 1. And then you factor out a 2 from the x, so it's going to just be x over 2 since you factored it out. So it's going to be minus -x over 2, something like that. Plus, now we're going to do the same thing on this one. I need that -1 to be a positive 1, again, because that's what the geometric series that we're using uses. So I'm going to pull out a -1 here, and it's going to be times 1 over, in this case, it's going to be 1 minus x. So if I distributed this -1 here, you would get this whole thing right here. You get where you started. Again, everything I did was just basic algebra. All right, so I'm going to move all this right here and transform it into a power series. So we have f of x being equal to, okay, so that one, first one is -1/2. So that first one is going to be the sum from n equals 0 to infinity. I'm going to zoom in a little bit here, and it's going to be times -1/2 times x over 2 to the n power. Okay. Then we're going to add this. So what I just did there was this part right here. Okay, now I'm going to do the second part right here. So I'm going to be adding this to, again, the same summation. Only this time it's essentially going to be -1 to the x to the n power, because it's just 1 over 1 minus x, which is in the same format as the geometric series, so that makes it kind of easy. Your r is just going to be that x. That's what I did right there. So you end up with an answer like this, but you might be thinking, is there any way to simplify this? You can technically simplify this in the following way. They both have the same summation, so you can just put the summation in front here. And you're going to end up with -1/2 times x over 2 to the n minus x over n. And that's the answer a little bit more simplified. Now you might be thinking, how do you find the interval of convergence for this? Well, what you can do is just figure out the interval of convergence of each individual summation. So I'm going to do this one and this one here. That first one, the r is x over 2, and that has to be between 1 and -1. Well, if you multiply both of those by 2, it's going to be on the interval from -2 to 2. Now, if you do the same thing on the second one here, this one right here, you're going to have x going from 1 to -1. So that interval of convergence is going to be from -1 to 1. And you're always going to want to use the one that is more exclusive. You're going to want to use the one that is smaller, because that -2 to 2 is going to be outside the interval of convergence for this one. It would diverge for that part. So since that part diverges, the whole thing would diverge. So you have to use the one that ends up being the smaller interval, which in this case, it's that -1 to 1. Okay. The -1 to 1 is included in the -2 to 2. So that's why you can use it. That's where basically both of the intervals of convergence for each piece of the summation match. So that's why you're going to want to use that. So your final answer for the power series ends up being this, what I'm highlighting right here. And the interval of convergence is from -1 to 1. So that's another representing functions using power series problem. If you have any questions about any of this video, let me know.